So, good morning. Welcome to Krishna's classroom. We continue with our discussion on autonomous systems. We introduce the concepts of what are called characteristics, singular points, and talk about the stability of the singular points. Now, these are all dynamical considerations of the problem. We look at the physical interpretation of this problem also. So, the system that we were looking at was this. Where we assumed P and Q are defined in some domain D. So, D is of course contained in R2, it's an open connected domain. Assume P and Q are continuous and the vector valued function Lipschitz locally in D. Now, D could be the whole of R2. Now, here T is the independent variable. And P and Q are explicit. So, that is what you call an autonomous system. That is, P and Q depend only on the dependent variables x and y. Okay. So, this is the initial value problem. So, we found that one where x naught y naught belonging to D has a unique solution YT, and at least to begin with, we say it is solution exists locally around the point T naught in a neighborhood of T naught. Then we looked at the possibilities. The possibility is that t is xt yt is defined for all t greater than or equal to t naught. So various possibilities we looked at. Xt yt or more generally something like on minus infinity to plus infinity, or from t1 to infinity, and so on. Or is not defined for some then of course we know that as minus 0 xt yt go to the boundary, or both. Now this is the general scenario that you have. Okay, now we are in a position, likewise you can and you have similar statement about the interval on which it is defined. Therefore, you see there are the various possibilities are it is defined on minus infinity to plus infinity, or t belonging to t1 infinity, or t belonging to minus infinity or where t naught belongs to each of these intervals. This is the general scenario that you have. Okay, now we define what is called a characteristic. And what we proved was that if xt yt satisfies 1, then satisfies 1 for tau constant. Of course, some conditions are satisfied, like x t plus tau, y t plus tau should belong to d, etc. So those conditions are there that you can work out. But what is happening is that if xt yt is a solution of that equation, satisfies that equation, and this is a consequence of the system being autonomous. Okay, so that much we have observed. Now we define what are called characteristics. See, if you look at this, okay, suppose you have a solution x1t, x2t, y1t, y1t. Suppose you have a solution x1t, y1t. Define t plus tau. Then x1 t1, so suppose where y0 x0 y0 is a point in D. Suppose this is the initial data that x1 y1 satisfies at t equal to t0. Then you see that because of this, you see that you get, so x2t is such that it's a solution, of course. What is the condition? You have x2 equal to so what is happening? x2 y2 obtained in this, defined in this way, is also a solution of the differential equation, but satisfy a different initial data. What is that initial data? It satisfies the initial data x0 y0 at t equal to t0 minus tau. Okay, right? So t0 minus tau is what? See, it's something like this. You see, it is quite easy to see the following. Suppose x0, suppose this is D and x0 y0 is a point, and suppose this is x1 y1. So x1 y1 at t equal to t0 is at x0 y0. Now what about x2 y2? x2 y2 is at x0 y0 at the time t0 minus tau. See, so this is another solution of the equation passing through the same point at a different time. Okay, so x2 y2 one satisfying the same initial data at a different time. Namely, t equal to t0 minus tau. So if you look at the dynamical situation, suppose you consider PQ as a, I'll give this interpretation soon, you see that this is as the, see, so the 2 has to be, because you cannot have two solutions passing through the same point, so they have to be identical. Okay, and what is the relation between x1 y1 and x2 y2? They occupy the same point with a time lag of tau units. So xt yt and x2t the same points in D with a time lag of tau units of t, tau units of t. Now this is the scenario, because you cannot have a say x1 y1 like this and x2 y2 like this. Okay, because you have only one and only one solution passing through that point. Okay, therefore the 2 has to be identical. So you are, so it's a, the dynamical scenario is, suppose there is a flow, this is a flow line, okay, or what you call a trajectory of a particle, then the one starting at x0 y0 at time t equal to t0 is followed by the one, another one starting at x naught y naught at a time t naught minus tau. Or I will put it this way, if tau is positive, then you see that the x2 y2 has already crossed this and gone. At t naught minus tau, it has occupied the point x naught y naught, and x1 y1 is following it after tau units of time. Okay, so that's the scenario. I will explain this out later. Okay, let us now define what is a characteristics. Assume that means xt not identically equal to some point, yt identically not identically equal to constant vector. Depends on t. Okay. That is both constants. Defines a solution of one with a continuously turning tangent. And the tangent is given by, that is what is happening is that, see, you take xt yt over t over the interval. You see that x dash t or dx by dt equal to pq this is pq, and p and q are assumed to be continuous. Therefore, what does it mean? It means this implies pq being continuous. Continuously turning tangent. Let me draw the picture. Suppose this is xt yt, and then you see that you have a tangent vector The tangent vector is given by P xt yt. Okay, so see, this is the vector. So this vector is given by this one. So this is the point xt yt. And you see that since P and Q are continuous, you see that both P and Q change as t changes continuously. So it has a continuously changing or turning tangent. Now this is called a characteristic. So what are the conditions? The conditions are that xt yt is a non-constant path. Okay, so it has a continuously turning tangent, then it is called a characteristic curve or a characteristic. So we have defined what it is: characteristic curve and characteristic. Okay. Now what we want to assert is this. There passes at most one characteristics. So one can easily prove this. If two characteristics pass through that, then they are identical. Okay. Okay. Suppose are two characteristics passing through x naught, y naught at t equal to t1 and t equal to t2 respectively. That means what you have is this: xi ti equal to x naught, yi at ti equal to y naught for I equal to now what we claim is that we show that x2t is identically equal to x1 t plus t1 minus t2. y2t now what you should see is that x1 t plus t1 minus t2, t1 minus t2 is tau, okay. So it is actually x1 t plus tau, y1 t plus tau, and you see that x1 t plus tau, y1 t plus tau is also a solution of the differential equation, okay. So you have x2t, so we observe that solution of 1, that is take t2. That we have already verified. Now you see that both x2t, y2t at t equal to t2 is the same as x1 t, okay, x1, okay, right. So we'll write it down. Okay, you make the following observation. Now x1 t plus is such that, which is already a solution of the equation, such that x1 at t equal to t2. So also so what do you infer? You have two solutions, constructed out of x1 y1 okay, and of course the given function x2 y2 is such that at t equal to t2 it satisfies this, okay, but now by the uniqueness theorem you have x2t equal to x1 because they both satisfy the same conditions. Therefore, if you consider these two, they are related, okay. So you see that through any point t there passes at most one characteristics. Identical and the representations with so you see that the characteristics and solutions are not synonymous. These are two solutions, x1 x2 y1 y2 are two solutions, okay, but if they pass through a single point then they are identical as a characteristic. There are two representations for this. So remark characteristics are not synonymous concepts. A characteristic may have several representations. Solutions. So we can choose a suitable parametric representation Now further remark, the above statement is not true if the system is not autonomous. In fact, they differ, the different representations are related, they differ by a phase difference. In fact, so we also make the following remark. The characteristic is a directed this is because irrespective of the representation, direction. So we shall now make this or go into the physical interpretation. Before that, we will introduce what are called singular points. Let x naught y naught be such that equal to 0. Suppose these two are, this is the situation. Then what happens? Then you see that xt identically equal to x naught, xt identically equal to x naught, and yt identically equal to y naught satisfies the equation. That's very easy to verify. So this is a constant solution. Where you see that it's a point which does not move at all. Such a point is called a singular point. Such a point is called a singular point. So it is x naught y naught such that, so it is x naught y naught such that P that's a definition of a singular point. Okay, it's called a singular solution also. You can call it a singular solution, there is no harm. Okay, it's quite different from the other solution with a continuously turning tangent. Okay, so we now go for the physical interpretation. So V is a vector xy. We can consider this. The differential equation is the system is defined when V is given. The vector field Vxy given. So this is as though, suppose this is your D, take a point xy, then you have a vector which is denoted by Vxy at the point. So what is happening is that at every point in D, if P and Q are defined, there is a vector field. So what you have is a field of vectors distributed over D. Now this is what the differential equation is. Now once this vector field is autonomous, means that it depends only on x and y, and let us consider t as the time variable and this as the velocity field. So let us take now we can consider xy as the position vector and Vxy as the velocity field defined in D. So you have two things. Now we consider xy as the position vector and Vxy as the velocity vector. At xy. So now we are coming to a dynamical picture. assume there is such a velocity field. Now a classic example is the river flow. If you look at the flow of river on the surface, you see that at each point there is a velocity vector. Okay, so if you mark the, suppose this is the river, at each point there is a velocity vector. In a sort of calm environment, we can assume that these vectors do not change their position with time, or you say the flow is an autonomous flow. Okay, that the velocity field does not depend on t. So at each time what we are assuming is that this velocity vector remains the same. It differs, it changes only from position to position and not with time. That is what we mean by an autonomous field. Okay, so we assume the velocity field does not change with time. And changes t variable and changes only with respect to xy. So that depends only on xy and not on time. That means there is a steady flow that you have on the river. Now if you take the analogy. Now what happens, suppose you have a steady flow. Suppose you drop a dry leaf, say, to make sure that it doesn't have a significant mass to change the flow line. It will be carried away by the flow. So it will take a path like this. So it starts, how does it flow? The flow lines or the path determined by Vxy is then a such that which is the tangent vector is Vxy, that is PQ. Okay, therefore this is the trajectory of a particle of a object subjected to velocity field. Like a dry leaf which floats, if you just drop there, it will take a path. Now if you want to be more visible, then you inject a dye at a point, then what happens is it will develop along a path, and that path will be the trajectory of determined by the velocity field V. And you see that this does not change. The trajectory are solutions. Okay, and one observes that these trajectories do not change with time. Because the system is autonomous. Okay, this is autonomous system. Does not change. The trajectories do not change with time. Okay, so you see, I can drop a particle here at time t1 and then it will follow a path. The trajectory has the property that its tangent direction at any point xy is given by so this is what you get. This is the most interesting part. So that's an interpretation. So this is as you see here, this one. So it follows a path such that at every point the tangent to the trajectory is given by the corresponding v. Okay. Now what happens, what I mean to say is this trajectory remains the same. So once the vector field is given, whether a particle is moving in it or not moving in it, or whether a leaf is dropped at a point and then you are observing the trajectory or not, there is always a path determined which does not change with time. Now this is what you call the characteristic. Okay, right? So irrespective of whether there is a floating leaf moving in the velocity field or not, irrespective of say floating leaf, is moving or not, there is a path determined by the velocity field Vxy which does not change with time. These lines are called the trajectories. Or flow lines. These are the various terminologies that are used for it. This is the dynamical scenario. Now you see that if a leaf is placed time t1 and a second leaf placed at the same point at time t2, with a time difference t2 minus t1, that means initially there is a time difference t2 minus t1. That time difference is always maintained by the two leaves. Okay, right? So one follows the other in the same direction along the same path with a time difference of t2 and t1. Okay. The singular point is the velocity is 0. Is called an equilibrium point. It's obvious. Once the particle is at x0, y0, there is zero velocity acting on it. So it cannot be carried from there. Okay. So x0, y0 is a point. If vx0, y0 is equal to 0, 0, then x0, y0 is an equilibrium point. Because if there is a particle there, it stays there for all the time. Because you see that xt is identically equal to x0, yt is identically equal to y0. If xt, yt is the position vector of the particle that you are considering, it remains at x0, y0 for all the time. Therefore, you call this an equilibrium point. That's the whole idea. So we have now given the physical interpretation for all the cases. Now we will be using both the languages. That is the language the physicists use, namely that the one corresponding to what are called trajectories or flow lines or what you call equilibrium point and so on, we will be using. And naturally now you can see with this physical interpretation, you can see now sort of questions that you have to ask. So characteristics are essentially the flow lines determined by the velocity field. It has nothing to do with a specific particle moving or anything, but what you call the solution is the path followed by a specific particle, and that traces what is called the characteristic. Okay, so through a point there is a unique characteristic. So all paths through that point are what are called along the characteristics. They do not deviate from the characteristic passing through that point. Now this is the dynamical scenario of the autonomous systems. Okay, now let us go into the discussion of what are called the different types of characteristics. Okay. Now we prove that no characteristic can cross itself. So you cannot have a situation something like this. Okay, this cannot occur. This is ruled out. Okay, so that's what we are going to say. C, which consists of xt yt for t naught, or what you call a half characteristic. This is a characteristic. I may be all sorts of things that we define there. And let then we have xt naught, xt1, yt naught, t1. Okay, then what do you have? Because of the uniqueness result. Now this implies C is a closed curve. That means what you are having is this. Okay, right? So this is the scenario that you have. So at T1 and T2, at T0 and T1, it reaches the same point. Okay. Now So that what you have is this, it will keep tracing the same path. Okay, therefore we can now define what is called the period. So C is and T1 minus T0. A okay, that means xt yt is also equal to x t plus t1 minus t0 and x y t plus t1 minus t0. Okay, so let us now define. So you have here x so now we define what is called a period of characteristics. Okay. H is called the period. H is the smallest number for which now there are many cases important physical problems where periodic characteristics We shall discuss this later. Now we define what are called isolated singularities. So we define what is a half characteristic. So if a half characteristic is the following, okay, so if C defined by xt by t such that t is greater than or equal to t naught called a half characteristic. Now various solutions may represent the same characteristic. Now remark, okay. Now we shall also observe that any characteristic defined for all t greater than or equal to t naught or t1 minus 0 where of course you take t1 t naught. This is the case approaches the boundary as t tends to t1 or it is either xt or yt or both becomes unbounded as t tends to zero. That's the situation now. What do you have? Now with this we observe the following. So we have the following lemma. What does it say? If a half characteristic is contained within a closed bounded region R, D, closed bounded region R in D, it is a compact region of D, then its representing solution is defined all t greater than or equal to. Now this is quite easy to see. Suppose something like, suppose this is D and this is R. Now you have a characteristic defined by a solution. At time t equal to t naught, it is here. Okay. Suppose x naught y naught where xt yt is a solution of the equation, autonomous system. Now what happens? What all things can happen? See, either C is defined for all t greater than or equal to t naught. Okay? Either we rule out the second possibility. The second possibility, see, if it goes to the boundary of D, then it has to get to the boundary of R at some time. Okay? Or if it, see, for the second alternative, C has to cross the boundary of R See, R is compact, that is closed and bounded region. Okay, this is your R. It has to cross the boundary of R. Okay, this is not possible since C is contained within R. So it simply follows you have the following scenario. What is it? C is because there will be some T1 at which it will cross the boundary, and beyond that it will not stay there. Okay, right? The second scenario states that there is some T1 where it will have to cross the boundary and get out of the region R, which is ruled out because we are given that the characteristic remains in R. Okay, therefore it is defined now for all t greater than or equal to t0. Now this is a very useful information. Right. Now we introduce some more concepts like what is called more about the characteristic. Okay. Right. So what you call an isolated singularity. Or equilibrium point. Is an equilibrium point and there exists a disk which does not contain any other equilibrium point. What does it say? Suppose this is D and this is an equilibrium point. You have got an R neighborhood of that. This contains no other equilibrium point, or any other equilibrium point is outside. Then you say x0, y0 is an isolated equilibrium point. For example, suppose you take P equal to then you see that 0, 0, an equilibrium point, it is isolated. Now you take a nonlinear case, take Pxy okay, just leave that. There are cases you can easily construct, not difficult. For example, you can take Pxy to be okay, wait. Now we define. See, what is important for us is to examine this scenario where the singularities or the characteristics, or we are interested in the behavior of the characteristics in the neighborhood of a singular point. Okay. So to determine to analyze the behavior of characteristics in the neighborhood of an equilibrium point. We make some definitions which are useful, which gives the right terminology for this one. Okay. Without loss of generality, we assume x naught equal to 0, y naught equal to 0 is a singular point of y. We say that a characteristic, a half characteristic, is approach the equilibrium point 0, 0 if zero. This is the definition. That means the limit point of x t y t is 0, 0. Okay, suppose you take this path. This is 0, 0. There is the path. This is C. Then you know that this approaches 0. Now we can define whether it approaches in a definite direction or not. So this is okay. We shall determine, investigate it approaches For that, what you do is consider the vector yt and we look at this, whether it tends to a so the question is diverges properly. This is the question that you are asking. So if this happens, then you say that, so if, see what is this? This is actually the direction, this is the slope of the phi t. So if the limit exists, or it diverges properly, or infinity, then we say that the equilibrium point. Along the direction of the limit. Okay. So what is it? You see that by it applies. Y derivative of t by which is the same as limit So you look at this, the limit of this. Okay. So whether it exists or not. So it's same as q by p, limit of q by p, whether it exists or not, or whether it exists or it diverges properly. Okay. Now this is what you call the direction in which it enters the equilibrium point. Now this, you will see examples of this discussed in detail in the next section. Now let me just, okay, so this is telling what happens to the particle or the object in future, but t is time, so changing t to minus t. Paths. Stability. Now we define what is stability. The last point I want to make here, there is not enough material for another lecture, so let me just conclude this. I know that it's already lengthy, but let me just conclude this with the defining stability. Okay. Stability. So let's equilibrium point. Isolate. We say that x naught, y naught is stable if given epsilon there exists a delta positive such that delta, that is xt yt at time t equal to t naught, for some naught implies norm of xt less than epsilon for every t greater than or equal to t naught. Then we say that Now this means the following. Suppose x0, y0 is the equilibrium point. Now you see, so you are given an epsilon. Okay. Then suppose there is a delta neighborhood of x0, y0, and suppose a characteristic C is at t equal to t0 here, then what happens is the characteristic will remain. So this is the point x0, y0. Sorry. So this is at some point, this is xt0, yt0. So at some instance t0, suppose the characteristic is inside the delta neighborhood, then it will remain in the epsilon neighborhood for all the time, for t greater than or equal to t0. Now this is what you mean by a stable equilibrium. Okay. So if any characteristic that passes through any point in delta goes to x0, y0, then it is always a stable equilibrium point. Now I think with these remarks I stop it. There will be more discussions on stability later.